Hello, welcome to Maths with EJD. In this video, I'll be talking about the SciPy.Optimize module under scientific computing with Python. Okay, this is the 18th video in that series. Let's go straight to it. As you'd already know, optimization is all about getting the best of every situation. And of course, this aspect considers the computational things you may have to do when optimizing different kinds of functions. So the SciPy.Optimize module is a powerful part of the SciPy library, and it is used extensively for mathematical optimization tasks. These tasks involve finding the minimum and maximum of functions, solving equations, and fitting models to data. And as you can agree, all of these things are extremely important for a scientist or for anybody in STEM and even people in other fields, right? The module provides a wide range of algorithms and utilities for different types of optimization problems, including linear programming, curve fitting, route finding, and general purpose optimization. We have this whole logistic thing these days. Like no country can survive without having a very strong logistics, like delivery of mails, delivery of food to destinations, and things like that. Okay, so let's look at the capabilities of the SciPy.Optimize module one after the other. Of course, as you already know, SciPy is scientific Python, which is a library in Python, and Optimize is a module under that. And of course, you're going to see different functions in that module that can perform different kinds of tasks. So let's go. The first one we are talking about is minimization. Of course, you can also take that to be, you can say minimization stroke maximization because, if you're minimizing a function, all you just need to do is to find the, take the negative of that, and then you get the maximum or something like that, depending on the particular case you're considering. Okay, so talking about minimization, we want to look at finding the minimum of a function. You have a particular function and you want to find the minimum value of that function. So, and a common problem in scientific computing is finding the minimum of a scalar function. The minimize function in SciPy.Optimize is designed for this purpose. So I think this requires highlighting. So what is actually doing that job is what you call the minimize function. The minimize function, which you find inside of SciPy, that needs to be properly highlighted. Okay, like you can see, so we use the minimize function in SciPy.Optimize, which is designed for this purpose. So minimize is the function inside optimize module in SciPy library that we use to minimize functions. So for instance, look at the objective function. You want to consider a simple quadratic function, f of x equals x minus 3 all squared plus 4. Normally, right, you can expand this function because x minus 3 squared is simply x raised to power 2, right? X raised to power 2 minus 6x plus 9. So plus 9. So if you now say 9 plus 4, that's 13. So if you expand this function, this is actually what it gives you. It's actually the same thing as x squared minus 6x plus 13 when you do everything together. So normally, if you're looking for the minimal values there, all you just need to do is differentiate x squared minus 6x plus 13. That will give you 2x minus 6. And 2x minus 6 is the same thing. So to minimize or maximize, you just equate that to 0. All right. So you have x squared minus 6x equals 0. That means, 2x minus 6 equals 0. That means x is equal to 3. All right. So x equals 3. So if x is 3, then you can put it back into this expression. That is 3 squared, that's 9. 9 minus 6 times 3, 18. That's minus 9. Plus 13, that's 4. So it means that the minimum value is 3 and the maximum is 4. That is doing it straightforward because it's just a simple expression. So we can even do that without even solving. By just looking at it, we can already do that. So you see, that's the kind of thing we want to now do with code. So of course, because we need to do some NumPy stuff, we need to, we need some array kind of thing in this case. So you need NumPy for that. And of course, from SciPy.Optimize, you import the minimize function. And then I think under control flows, I must have talked about functions. I think I talked, or was it in another video? I talked about functions and modules. So we see that coming to be very useful here. I want to put the line numbers so we can see the numbers. Okay, good. So in line 1, you import NumPy as NP. In line 2, from SciPy.Optimize, you import minimize, and then you define the function in lines 4, 5, and 6. So we call that the objective function, which takes the parameter x, right? And then it's returning the value of x minus 3 or x minus 3 squared plus 4, right? So then the initial guess, of course, when you optimize this kind of thing, right, you expect to get like one value, right? If you optimize a quadratic function, you're going to get a single value, because when you differentiate, it goes to order 1. All right. So here we have an array of the initial guess. So x naught, you just say x naught is 0. That's the initial guess. Then of course, I think you understand this initial guess better when we take other examples. So in line 11, so this is where we actually perform the minimization in line 12 now. So you just say result is a variable name, which is assigned to the minimize function. So you are minimizing the objective function x minus 3 squared plus 4, subject to the initial condition 0. All right. And then, so line 14 is giving you the optimal value. That means the y value, the optimal point is actually the x value. From what we did before, the optimal point is actually 3, because when you differentiate this, you get 2x minus 6. And that means x is equal to 3. So it means the optimal point is your 3. And then, okay, I think I forgot to do something. Let me clear all outputs. I should have done that since. Yeah, good. Yeah, great. So when you differentiate, right, x is 3 already. If you put the 3 back, you get 4. And so the optimal point is the x value. The optimal value is the value of y. So, and all of that is extracted from this result. So from result now, so result.x, that's the optimal point. Result.fun, the function, that's the y value, because of course the function itself, the original function is y, which is f of x. And that is so whatever you get when you put the value of the x value back, the optimal point back into the expression, that is your optimal value. So when you run this now, you get those results. So the optimal value is 4. Never mind, I think some, of course, the zeros are too many, so you don't care about everything that comes after. Just focus on the 3 and 4, like that, So that's some computational thing happening right there. Okay, so as you can see, this model is simple. The function is simple enough for us to just do direct minimization. Just differentiate, equate to 0, get the value of x, and whatever value you get, put it back into the original function, and then you get the optimal value. So that goes. So we go to see more and more difficult things afterwards. So in this example, you can see that the minimize function successfully finds the minimum value of 4 at x equals 3. So I like to highlight this. It's not just a thing, it's actually what is getting the job done. That's why I like to, highlight it that way. Okay. Then we have curve fitting, right? Curve fitting. Now, curve fitting is one very sweet thing I like to do. It's like you have data, and then you want to fit it to a particular curve of your choosing. And what that is doing is you're getting the constant values. In this quadratic expression, now y equals ax squared plus bx plus c. When you fit a curve to this, now it is going to spew out the values of a, b, and c that makes it conform to the data you're fitting it to. All right. So fitting a nonlinear model to data, for instance, that's what we are doing here. And then you see, curve fitting is the process of finding a curve that best fits a series of data points. So the curve fit function, rather, from SciPy.Optimize is used for this purpose. And then let's look at a sample so we can consider. Okay, so let's look at a data model we can consider. So suppose, okay, let me put this way. Okay, suppose we have some noisy data that we believe follows a quadratic model, y equals x squared plus bx plus c. So now let's jump into it. So here now, of course, we need NumPy. If you remember also, you discover that we said that SciPy is built on NumPy because we need arrays, and NumPy is the master of arrays and matrices like that. So you see us always referring needing the help of NumPy. So import NumPy as NP, and then from SciPy.Optimize import curve fit. So curve fit is what is going to do this curve fitting we are talking about here, and then in this case, since we are fitting data to an equation, it is important to see how well the data fits the function, right? So we have to define the model function. So here now we have define model x, that's like that's the variable, the independent variable. Then ABC are the constants which we need to estimate from the curve, right? And then in 9, we are generating some data. So the x data is actually is from -10 to 10 in 100 divisions, okay? And then we have the y data. The y data now is 3 times x data. So it's, of course, we have 3x ax squared. So the y data now is 3 times x squared minus 2x data plus 1, right? So this is actually, this is like you're generating data from a known function, 3x squared minus 2x plus 1. And then you're adding the random normal size of the x data, right? So that is the kind of data. I'm going to get to a point where I show you actual data, some data in Excel sheet, and we are using that for something close to this. So I think that'll come down the line. So, but from here, we are generating x and y data from a known function, 3x squared minus 2x plus 1. Of course, here the x is actually x data, because that is what we declared in line 10. So let's talk about the actual curve fitting, which is happening in line 14. So perform the curve fitting. Of course, we need the parameters. The parameters here are A, B, and C. Then we need the covariance. And then, so you use the curve fit. So you have curve fit of the model. So, the model is a function you've defined up here. X data is what you have here, and Y data is what you have here. And then once this is done in line 14, the next thing you have to do is to extract the parameters ABC. And then in line 19, now you are printing the fitted parameters. So the values of A, B, and C that makes the curve fit to the data generated in lines 10 and 14. You are going to get those values. And then from 21 to 25, that's what you have. We are looking at the X data and Y data, and then we are looking at the model data. So we want to see how the data fits with the model like that. So let's see how that works. So that takes a bit of time, and you can see, so the parameter values. So it means that if you want to fit the data generated from lines 10 and 11 to a quadratic expression, it means that the value of A has got to be 2.9968, blah, blah, minus 2 point something, something, minus 2.018, like that, 1.2169, and so on and so forth. And you see that the fit is looking very perfect. The actual data are these blue stuff, but the fitted curve is actually red. So you can see everything sits almost perfectly well together. So, and the beauty of this is that probably you have data from some kind of experiment, and you feel that the data follows, it follows the shape of a parabola. Like maybe it comes, it comes from the negative side, and then it comes to 0, and from 0, then it begins to rise again. If that's the kind of thing you're having, for instance, maybe when the temperature is negative, the thing is up, and then as you're increasing the temperature and it gets to 0, the maybe a reaction, so to speak. Maybe there's a reaction like that, and it comes to that point. And by the time you begin to increase the temperature again, the temperature keeps the reaction keeps rising again. It may not be a reaction, it may be some phenomena that goes in this form. So if you know how that behaves, then you can already get, oh, okay, I think this looks like a quadratic thing. And then you just need to now get the parameter values A, B, and C, so that now the quadratic expression will have to be something like 2.9968 x squared minus 2.0186x plus 1.2170. So, and with that new equation, it's like you now have a model that, so from that experiment, you can now use that to always, measure, to get values for what, if you have a particular X value, you can already say what it is, because now you have got that model from empirical data. Okay, so the plot shows the noisy data points and the fitted quadratic curve, demonstrating how curve fit can be used to determine the parameters of a model. So that goes. So the next thing we're talking about is root finding. Root finding. So this is basically talking about solving equations. So you want to find the zeros or the roots or something of any given equation. So SciPy.Optimize helps you a lot with root finding. So, for example, solving an equation. Root finding involves solving equations of the form f of x equals 0, and then the root function here, again, the root is the key thing we are using here. So the root function is the function inside that module that gets inside the SciPy.Optimize module that gets the job done. So that is what it is designed for. So imagine the equation x cubed minus 6x squared plus 11x minus 6 equals 0. Now, because it is an equation of degree 3 because of the power 3 on top of x, it means that normally you should have 3 results. But when it comes to computation, right, one of the reasons why we do numerical stuff is because sometimes some equations are difficult to solve analytically. So you can now come up with some of these methods to try to see what you get using computation. For instance, now the answer, so there are 3 possible answers because it's of degree 3, just like I said already, and some of them can even be imaginary. I think I already did something on imaginary. Yeah, I have a playlist ongoing on imaginary numbers, so on complex numbers actually. So whatever you get from this equation is going to be determined by the initial guess, and that's why I'm going to try like 1 or 2 initial guesses to see what happens. So from here now, of course, line 1, we need from SciPy.Optimize, we import roots because that is the function that gets the job done in this case. Then you define the function itself. So define equation, and that is x cubed minus 6x squared plus 11x minus 6. Don't forget, the way to do exponentiation in Python is to use double star. 1 star is multiplication, double star is power, whatever. And then in line 7 now, we have line 8 is the initial guess. So if our initial guess is 0.0, so we can now find the roots, and to find the root, that's what is happening in line 12. That solution is equal to root of the equation you have defined here, the function, and the initial guess you have, which is x naught. And then you can run that and you get the root, and the root here is actually 1. So it means that one of the solutions to this problem is 1. Don't forget there are 3 solutions, but because of the initial guess you have used here, you're getting 1. Okay, so let's try another initial guess. Okay, let's try another initial guess. Let's say the initial guess is now 10. So instead of 0, so like I said, the initial guess determines what you get. So instead of 0, like before, we now have 10. So if I use 10, see what I get, 3 now. So it means 3 is also one of the solutions to that equation. Okay, so I mean, that's something. What if I try with a negative value and see that thing might actually have a negative solution? We have got 1 and 3 as possible solutions. What if I say minus 10, for instance? Let's see what that gives. I'm not sure. Okay, it goes back to that one. Okay, let me experiment and say like minus 5. I know minus 5 is likely going to give 1 again. Okay, it's also giving 1. Let me say now, let me just say 5. Let's see what that gives. 5 also gives 3. What if I go 15? Let me see what happens there. 15 gives 3 too. Okay, okay. Let me see. What if I say 0.5? Let me say 0.5. What happens? That gives 1. Okay. Yeah. So, yeah. So those are what we have for now. But of course, I think this looks like an expression that can be solved analytically, So we already know that for that function f of x equals x cubed minus 6x plus 11x minus 6, 2 possible roots are x minus 1 and x minus 3. So by dividing it by the product of x minus 1 and x minus 3, we can actually find the other roots, But we need an appropriate initial guess. Okay, let me even do a crazy initial guess and just see what happens. Let's say 100. Okay, it's still 3. Okay. What if I say minus 100? Let's see. Okay, it still comes to 1. Okay, so I mean, that's what's happening there. Okay. Yep. Of course, there are other techniques you need. Probably if you need your answer to be within a particular range, you're going to see those kind of possibilities later. Then we come to a very interesting aspect, which is linear programming. And this happens a lot in different sectors, right? For instance, in business, right, you can actually come up with a linear programming problem based on the peculiar solution problems you have. Probably you make two products, right? You make two products, and the reason for linear programming is because things don't always, there are constraints, right? Maybe you have all the raw materials you need, but you don't have enough labor, or you have all the labor you need, but you don't always have enough energy. So there are some kind of constraints in the production process, right? That is why linear programming problem is cool. So here now, you actually want to get the best result given whatever constraints you might have. So for instance, you want to solve a linear programming problem. Linear programming involves optimizing a linear objective function. So, linear means that x, the power of x or y is 1, and then x, you don't have x and y multiplied together. That's why it's called linear programming. The highest power of either x or y is 1, and then you don't have the product of x and y as a term in the expression. So linear programming involves optimizing a linear objective function subject to linear equality and inequality constraints. So the linear programming function in SciPy.Optimize handles this. So the linprog, that's what you need inside of SciPy.Optimize to do the job. So for instance, you want to maximize 3x plus 2y. Let's say that you have two products. Product 1 is x and product 2 is y. So what you want to maximize, probably you want to maximize profit. For instance, you want the best profit you can get with all the constraints. So if you produce 3 of the first product and 2 of the second product, like that. No, no, that shouldn't be. Maybe the cost, right? Let's say the cost of manufacturing the first product is 3, and the cost of manufacturing the second is y. So your profits. No, this won't be the best thing. Probably, to get profit, right? Profit is revenue minus production cost. Revenue minus production cost. So maybe your revenue minus production cost ends up giving you 3x plus 2y. And then you want to get the best of this, subject to the following constraint that, x plus 2y is less than or equal to 20. That's a kind of constraint that, say, if you 1 unit of x and 2 units of y, like that, you cannot, you have something in particular, maybe labor or whatever it is, and it is less than or equal to 20. You can't get more than 20. Probably you may need up to 50 of that, but the best you can get is actually 20, and then if you have 3 of x and 1 of y, you have the sum of that together would be less than or equal to 30. So that's some kind of constraint. And then, of course, x and y are not allowed to be negative. They have to be positive. Of course, if you're talking about maybe number of items produced, of course, it can be negative. So let's see how we present that as a linear programming problem. Okay. So first of all, we need the linprog function from the SciPy.Optimize module. So from SciPy.Optimize, import linprog. So you have the coefficients of the objective function. So for the objective function now, so you take it as 3x plus 2y, and then, you take the negatives of this. That's -3 -2, put that there. And then for the constraint now, you have 1, 2, 3, 1. You have that matrix on that side. And then the constant of the inequality constraint, that's b, which is 20 and 30 here. So you have two parts now. You have the objective function, and you have the coefficients of the constraints. And of course, you have the right-hand side of the constraints. And then, of course, there's a bound, right? There's a bound that x and y must be greater than or equal to 0. So from 0 to infinity, so to speak. For y is also from 0 to infinity. And then the actual linear programming is done in line 18, where you say, result is just a variable name here. So you now say linprog with this c now, c, then you have AUB is A. That is the upper bound of A. No, AUB is this A, this matrix. Then BUB is this B, right? Like that. And then you now have the bounds, X bounds and Y bounds. And then if you run this now, you get the result. Now, to solve this problem, like you may need to use something like simplex method or something, and it can be quite tedious, right? It can be really tedious. But I mean, so here you can appreciate the computing because if you have to do it manually, it takes a lot of time. But then because with this linprog, it's all done within 5 seconds probably, and then that is what you get. So you now see that the optimal point, it means for optimal point now you need probably 8 units of x and 6 units of y, to get the best profit you can make is 35, I mean roughly 36. So in this example, limprog, okay, let me do my normal issue of highlighting the function that is doing the job, like the man of the match, so to speak. So in this example, limprog finds the optimal solution to the linear programming problem with an objective value approximately 36. So that's like the maximum profit to make maybe $36,000 or whatever at the point where X is 8 and Y is 6. That's what's happening there. So if you solve this manually, that is what you should end up getting. So that actually works. So let's talk about constrained optimization. So in this case, we have something like minimizing a function with constraints. Okay, so in many real-world problems, we need to minimize the function subject to constraints on the variables. So the variables themselves have constraints on them. So the minimize function in SciPy.Optimize can handle such a constraint. We have seen minimize before. That the first problem we solved, we used this. So now we have the objective function f of x y equals x squared plus y squared, and then the constraint is x plus y is greater than or equal to 1, and then x and y each are positive, like greater than or equal to 0. Okay, so again, we bring the minimize function out, and then here we have the first one, you have x naught squared. So x of 0 here is like our x, and x of 1 is our y. So x0 squared plus x1 squared. Then in line 7, 8, 9, you define a constraint function. The constraint function here, so I think this is a big deal now. So you have x naught plus x1 minus 1. So it means you transfer this 1 here. So you have x naught plus x1 minus 1. That comes. And then constraint dictionary. So you define a constraint dictionary. So you have the type is inequality because greater than or equal to all these ones are inequality. And then you have the function is actually a constraint 1. So the constraint 1 here is actually the function here. So a dictionary, right, is actually a key value pair. So the key is type, the type is inequality, the value. Then the function is constraint 1. That's defining the function. And then you have the bound 0 to none, as usual, because x and y are greater than or equal to 0 each. So you have 0 to none. And then the initial guess. So here you need initial guess. And this chose that to be 0 0.5, 0 0.5. So this can actually be anything. So you can play with different initial guesses depending on the kind of results you want. And the actual minimization is happening in line 19. So you have the objective function, which you defined up here. You put that here. And then, of course, you have the x naught, which is the initial guess. And then the method here is SLSQP. It's a method for minimization. You can check that up, SLSQP. And then you have the bounds and the constraints. And then you just get this result in one blow. So to do this manually, it may not be that easy. What if we change the initial guesses here to 0, 0? Let's see what happens. What happens? Okay, still something pretty close to what was before. So what if we say it is 1, 1? What happens? You can play with different. That one thing with computing is that you can quickly play with different values and see what goes. What if we say 10, 10? Just playing with these things and see what happens. Okay, so I mean the value is around the same thing with almost every kind of initial guess. So that goes. So in this example, the minimize function finds the minimum value of the objective function subject to the given constraint, which occurs at x equals 0.5, y equals 0.5. So x this, y this, and then the optimal value itself is actually 0.5. Of course, that makes sense, right? Because 0.5 squared plus 0.5 squared, that's like 0.5 plus 0.5. So that ends up at 0.5. Then we talk about global optimization. So finding the global minimum of a function, for instance, for functions with multiple local minima, global optimization algorithms can be used to find the global minimum. Now, for instance, there are some functions. Like if you have a sine graph now, a sine curve, you can see it is sinusoidal. It goes up, comes down, goes up, comes down, and that happens endlessly. So at some point you want to find the highest maximum or the lowest minimum. So that's global maximum and global minimum. So if you need that kind of thing here, so the Bayesian hopping is what you need in that kind of case, or is it Bayesian hopping, I should call it. So the Bayesian hopping and differential evolution functions in SciPy.Optimize are useful for such tasks. So you want to find the objective. So the objective function here is just f of x equals sine 3x plus x squared. So, of course, this sine 3x already tells you it keeps on going on and on, like it's endless. So, but then you want to find the global optimized value. So, And then, of course, you define the function again. Of course, you know, to get sign, right, you need it coming from NP. So because we have imported NumPy somewhere, we don't need to bother again. But if this is the code, in fact, let me do it here to avoid confusion in case you're running this alone. So normally you should import NumPy as NP because you need sign, and sign only comes from that NumPy. So you define the function np.sign 3x plus x squared. And then the initial guess here is 2. We are also going to play with the initial guess and see what happens. And then, of course, the actual global optimization is happening in line 12, where you use Bayesian hopping function, of course, which has been imported from SciPy.Optimize already, subject to the initial condition x.x0. And then we can get the x and y values. So that's minus 0.42, blah, blah, and minus 0.77 something. So what if we say the initial condition is 20? What happens? Okay, we get about the same thing. What if we say it is 0, 0? Let's see what we get. Okay, it's about the same result, still interesting. So, I mean, that goes. So it looks like it's the same for every kind of initial condition you use. Import numpy as np, numpy as np. Okay, so that goes. So we can see that for all. Okay, or let me go negative and see what happens. Probably we can get something else. Okay, well, yeah, I think it's not strange actually, because we are looking for global minimum or so. So it means that whatever happens, this is the lowest value you can get for x and y. So, and that's why the initial condition doesn't actually matter. Okay. So in this example, Bayesian hopping is used to find the global minimum of a non-convex function, which has multiple local minima. So because of the sign now, you can say that the minimum values are many, but we want to see which is the lowest of them all, like that. Okay, let's talk about nonlinear least squares. Nonlinear least squares. Fitting a nonlinear model. When the model to fit is nonlinear, the least squares function can be employed to perform nonlinear least squares fitting. So for instance, you have this model, y equals ae raised by bx plus c. And you want to fit this to data. So just like what we did before, you know, so you declare the model, you know, the independent variable is x, and then you have the parameters a, b, c. Now, the other time it was quadratic. Now it is, you have something exponential like this. So you define that exponential function np. Ex becomes from numpy again. So don't forget, if you are running this alone, because we have done numpy before, we don't have to worry. But, you know, because of newbies, I may just want to start this, import numpy as np, because you may be having error issues in case you're running this all by itself. Okay, I've even run it, but I just want to explain all these parts. Okay, this. So again, we define the function, then the residual function, right? Because we want to use least squares now. So, and the least square takes the actual value minus the model value, you know, so that difference is, we want to shrink it as much as possible to be sure that the difference is not that big. And then the data we are bringing is actually just like the kind of thing we had before. So you have x data dividing 0 to 4 into 50 equal divisions, and then you have y data to be 2 exponential 1.5 x plus some random noise like that. And then here we have initial guess to be 111, initial guess for the parameters a, b, c, that is. And then, of course, in line 20, we are doing the least squares fitting. So with residuals, initial guess, and the arguments x data and y data. And then, so we can now extract the result in a, b, c and print the fitted parameters. And of course, it's good to visualize so we can see how well the fit is doing. And the fit looks exactly perfect. And it tells us that the expression now should be like y equals a raised by bx plus c should now be like 1.9945 e raised power, say 1.505010 x plus now, or minus 0.0476, like that. So that's what that is telling us. So, you know, you have your data and you fit it to this expression. So you can now use this new formula to, you know, get the value of this stuff anytime you need to use it. Okay. So what I'm doing here is, instead of using the data from, you know, this x data, y data from a function, so I'm doing the same thing with particular data. Say maybe you did a measurement and the x values are all the 0.1, 0.5, and the y values are all this. So we are fitting it to the exact same expression, which is still defined the same, a e raised power bx plus c. So now with this kind of data, so you have something like this. So, and then you have another set of coefficients like that for the parameters A, B, and C. Okay. So that goes. And of course, here now, what I'm doing is I'm actually bringing a real data, which is called the time series interpolated data. We talked about interpolation in the last video. So I did some kind of interpolation on the document the document I showed the last time. I think I have it right here. Hope I still have it. Good. So, I showed something like this when we're doing linear, when we're doing what was that now? Interpolation, yeah. So you can see all those gaps missing, right? So I used the method with length there. I used the method with length in interpolation to now interpolate so that, instead of having, okay, yeah, you can see now, okay, if I open this up. So you can see those gaps are still here, right? But then after interpolating, I got this result in sheet 2. So you can see now that every value is now filled up. Anything that was empty is now filled up. So that's the work of the interpolation we did in the previous video, which you can refer to if you have not seen it. Okay, so I have interpolated now. So I want to use this data to do the same least square thing I've been talking about, right? So I go back to that. So all I'm doing now is I'm just, instead of, so you can see where we are coming from. In the first case, we used a function, an exponential function, to feed the data with some noise. That's why the random is there. And here now we have some discrete data. And in this case, I'm uploading the data from a file, an Excel file called time series interpolated, and I'm fitting it to the same function, to the same function bx plus a raised by bx plus c, right? And then of course in that folder we have date and value. That's why the thing is a bit extended. So of course the scaling and all of those things are done. And then now if we fit that, see what we get. This takes a bit of time because I'm dealing with okay, so you can see, look at what the data looks like. So the fitting is now different. So, and of course you can see the parameter values are also different because we are dealing with some kind of data that is a bit chaotic like that. So that actually can happen. Okay, I mean, if you want to make a bit more sense of this, you can actually, sometimes I like to use simlog. So if the data is so if the scale is large, I just say plt.y scale, and I just do that in sim log like this. And if you run that again, it gives you, okay, now you can see the data looks really, really chaotic, but at least we have succeeded in getting a fit for it like that. So that's the kind of thing that is happening there. Okay, we can also do multidimensional root finding. For instance, solving a system of nonlinear equations. When dealing with a system of nonlinear equations, the fsolve function, okay, fsolve function, the fsolve function is a robust tool. So for instance, you have x plus y squared minus 4 equals 0. Of course, you can solve this manually and it will take a bit of effort to get your result. But then with this SciPy.Optimize, you can get that done too. So define the system of equations, x, y, the variables, and then equation 1 is x squared plus y squared minus 4. Equation 2 is x minus y squared. That's coming from here. And then return the equation 1 and equation 2 based on whatever variables you have supplied. And the initial guess is 1.0, 1.0, which you can play with. And here, fsolve is what you use to solve the equations with respect to the initial guess. And then you just get your solutions. Okay? So the solutions are 1.56 and 1.25 for x and y respectively. So what if we make the initial guess 0, 0? What do we get? Do we get the same result? Let's say, okay, now this is, the result is 0, 0 here. And then it comes with a warning. So maybe that's not a good initial guess. That's what that is. What if we do 0 0.5, 0 0.5, 0 0.5, 0 0.5? Okay, that gives us 1.56 and 1.24. So close to that again. What if we do 5, 5? So you can always tweak all this initial guess to, okay, it's still about the same thing. What if we do 50, 50? Is it going to make any sense? 50-50, is it going to make sense? Okay, it still stays at that value. What if we do 10-10? You know, it was initially 1-1. What if we do 10-10? Does it change anything? I suspect it's going to be about the same thing. So, I mean, that's that. Okay, so in this example, let's find the solution to the system of nonlinear equations, demonstrating its capability to handle complex root finding tasks. So you can do a whole lot with this. Then you have the bounded optimization. So meaning a function with bound constraints, minimizing a function with bounded constraints. So like you want to minimize a function, but the value of the function has to be within a particular range, a particular limit. So when minimizing a function, you might need to restrict the variable to lie within specific bounds. So the minimize function can handle so you can see the minimize is coming up again. So it's the minimize function does a lot, right? Does a whole lot. So you don't want to joke with that kind of function, right? So here we have the objective function f of x equals x squared plus 10 sine x, and we want the value of x to be between minus 10 and 10 because you know this can go all the way down to maybe negative infinity to positive infinity, but we just want it within a particular range, right? So, and we want to find the minimum value. So again, we define the function, then we have the initial guess here, it's 2, and we have the bounds minus 10 and 10. X lies within that bound. And then the actual work is done in line 15, where we have, so you say the result, minimize objective function, subject to the initial guess, and then put the bounds. And then in one blow, you get your results. So the optimal point, as the X value is 3.83 positive, and the y value is 8. So that's the maximum, the minimum you get from that place. So what if we change this to say 20? What happens? Okay, it gives us something negative like that. Of course, I don't think we should be going beyond minus 10 or 10 because we already have a boundary for that. But even if we do this, this is what we still get. So that works. Okay. So the capability is so serious. So what about minimization with multiple constraints? So you want to minimize the function with multiple constraints. So it's possible to have both inequality and equality constraints in the same optimization problem. So that's like what we call mixed constraints sometimes. So you want to minimize maybe x squared plus y squared, which we call x of 0 squared and x plus 1 squared here. And we have constraints, you have an inequality constraint, x of 0 plus x of 1 is less than or equal to 1, and you have x of 0 to be greater than or equal to 0, and you have x of 1 is greater than or equal to 0, and then x of 0 minus 2x of 1 is equal 0. So you have inequality constraints and you have equality constraints too. So again, you just throw all of that in here, and then you get all these. So you define the function, then you define the constraints also, one after the other, you know, as different functions on their own. And then then you talk about the constraints too. So what kind of constraint do you have? The first one is an equality constraint, as you can see. This is so the first type, you know, constraint equality. Oh, sorry. The equality constraint is this last one, right? So the equality constraint is the last one. So that's why you define it as x of 0 minus 2x1. So the first type, you have type equality, the function, that's constraint equality. The next one is you know, you have an inequality constraint, and the way to express that is you have 1 minus x of 0 minus x of 1, like transferring it to the other side. So that's what you have here, and it says, and every other thing is actually an inequality constraint. So you just put their names 1, 2, 3 like that, and then you have your initial guess 0.5, 0.5, because we have x of 0 and x of 1, and then you minimize in line 30, and then you click on that, and then the result just jumps out at you like that. So you get your x of 0 is minus 2.22 times 10 raised to minus 6, and x of 1 is minus 1.1 times 10 raised to minus 16. And then the optimal value, that's the optimal expression, like the function is going to be 6.1629 or 30 times 10 raised to minus 32. So finally, this takes us to the brute force optimization. Now, brute force tells you normally to get the optimal value here is not that easy, but then you want to do something, you want to do some, you want to go some extra mile. That's the idea. So finding the global minimum using brute force search. For functions with multiple minima, a brute force search can be used to ensure finding the global minimum. The brute function is suitable for such tasks. So there's a brute function inside SciPy.Optimize, you know. So we have a function called brute. So for this, So you have f of x comma y, which is equal sign x plus cos y. And we want to find the global minimum of this. So again, you define the function. Of course, NP comes from sine and cos comes from numpy. Don't forget. So you have import numpy from numpy as NP. So normally I don't have to do this because we have declared numpy before, but in case you want to run this all by itself, it's important to take note of that because it won't work if you don't do that first. So you have np.sine x, that's x of 0 plus np cos y. So x is taken as x of 0 and y is taken as x of 1. Then you define the ranges for the brute force search. So you want the range for which the values will come. So the ranges you now slice -5 to 5, 0.1, slice -5 to 5, 0.1 for both x and y together. Then you can now perform the brute force search. So you say result is brute, objective function ranges, full output true, and then you print the values of x of 0 and x of 1. And that is what you get. Of course, you can vary that by varying the ranges also. So like that. So you can see each result. So for the first one, x is 4.7124, which is between -5 and 5. And this is also -3.141, which is also there. So what if we can also extend the range and see what happens? So if I come now and say this is -10 to 10, and I want this one to be between -3 and 3. Can we get a result for this? Okay, I mean, that happens. So we have we have something for that. So your range determines what you get here. So wow, this is such a lengthy one, and I know you really want to sit with it and try it. Don't forget the notes will be up. You're going to find the notes by clicking on the link in the description box, so you can practice hands on. Don't ever forget. And then of course you need to uh sign up, subscribe, and hit the notification bell so you can get alerted when another video is uploaded. And you definitely don't want to miss this because these are very useful tools in scientific computing. So don't forget to subscribe, hit the notification bell, comment, tell me what you like to learn, or if you have questions, then of course always share with others, and we'll enjoy all this together. Thank you so much for always coming over here to learn. See you in the next video. Bye.